we are starting at 12 meters per second. This is our initial velocity. And then changing to 5 meters per second. That's our final velocity. 5 meters per second is definitely going to be less than 12 meters per second. And so it must be slowing down. That is correct. And the type of acceleration that would be is, again, anytime we have a decrease in acceleration, generally that is going to be what we call negative acceleration. So this one is correct as well. Great job on that, everyone. I'm going to go ahead and send out the links to your notes. Here's the link for Larkin students. Here is the link for Bengal students. And again, one link will work, one won't. So just make sure to click on the one that does work. And then otherwise, you can also get to it from your grades tab. If you want to start raising your hand, letting us know that you already have that open, that is awesome, because that'll help us a little bit later. So go ahead and get those hands up once you have it ready to go. Remember, the reason we want to be doing our notes during class is because if you do your notes outside of class, right, so a reminder here that notes outside of class means that you only get notes credit, whereas if you do your notes during class, and you have to pass, in that case you get both notes and attendance, credit. All right, so we do need tangible evidence that you are here and participating. That means you're responding to the chat. That means you're raising your hands when asked, as well as we actually need you to be doing the notes and passing them during class. Awesome. All right, so again, raise your hands once you have those open and ready to go. I will expect 100% of you to have raised your hand or responded in the chat by the time we get to slide number, 7. All right, let's go ahead and talk a little bit about our reminders. Please do not share contact info. Please participate often and well and behave appropriately. Don't forget that these sessions are recorded and distributed for learning purposes. We are at day 11 out of 60. We are 3 days away from spring break. Tell me in the chat if you have any plans for spring break. Today we're going to be talking a little bit about friction and gravity, a couple of other forces as well, but the main ones we're going to be taking a look at today are friction and gravity. Let's go ahead and take a look here. We're about a fourth of the way through our unit here, so this is where we will be going. You'll see that we're going to be getting into Newton's laws in our next lesson.
All right, so today we are going to be going over a lot of definitions, but that's okay. We'll take it one step at a time. We're going to be able to define stuff like gravity, something called normal force, applied force, and the friction force that will involve something called static and kinetic. All right, we're going to identify forces on a diagram. So all these forces aren't going not to be for nothing, but we're going to, on a diagram, show which direction they're pulling or pushing and how they interact. All right, so let's get started.
Let's go ahead and get those notes open. As mentioned, I do expect everybody's hands to now be raising up or sending me chats. I know, Lena, you sent me a chat. Awesome. So go ahead and open up those notes. There's the Larkin version. There's the Bengal version. One will work, one won't. So make sure to try both. Otherwise, you can go to your grades tab, the content tab, or the plan tab. So I'm going to go ahead and do a little bit of a trick for you. This is always a fun trick to show your friends. It's a little bit of a magic trick. All right, so I'm going to go ahead and share this with you up on the board. Let me go ahead and change this to presenting. Awesome. All right, so let's go ahead and take a look here. All right, so taking a look here, I have a cup. All right, I have a penny, and I have a card here. All right, we're going to see how well I can do this. Sorry, I'm going to use something else too. There we go. Perfect. Okay, so we're going to go ahead and see what happens when I do this trick, and let's see if I can actually do it correctly on the first try. All right, ready? Here we go. All right, what did you notice happen? Tell me in the chat. I can go ahead and try it again in case that was too fast. Again, I will try to fix this camera. Come on, camera. There we go. All right, what did you notice happening? All right, tell me in the chat. Tell me in the chat. Yeah, excellent. So what we can see here is that when I flick the card here, the penny actually falls straight down and lands in the cup. Smiley faces emojis in the chat box if you saw that. Right, so as I flick the cup here, right, we can see the penny actually drops straight into the cup. The penny drops straight into the cup. Thank you, Cody. Thank you, Lena. Thank you, Shayna, Tim. Excellent. All right, so let's go ahead and talk a little bit about this. So what do you think is pulling, oh my goodness, I'm so sorry, I just dropped my webcam. What do you think is pulling the the penny downwards. All right, tell me in the chat box what makes things fall. Yes, 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 exactly. So gravity is actually what is pulling down this penny, all right? Now, what's preventing the penny from falling, though, initially? Initially, what object is making the penny not fall? So initially, why is the penny not falling? Yeah, the card is in the way, right? So the card is blocking the penny from falling. Now, what made the card move? So physically, how did I get the card out of the way? Tell me in the chat box, what did I have to do to move the card? Yeah, I didn't actually pull it. Pulling it would have been a little bit hard, but I did use my hand in order to flick it. Yeah, right? So I pushed on it, I think might be a little bit more accurate to say, and I pushed on it very quickly, right? So I flicked the card. If this thing will let me type, right? I flicked the card with my hand, and that is actually what removed it from underneath the penny. And then once it was removed, we already determined this, once it was removed, the penny fell, right? Sorry, these tools are being crazy. The penny fell. Now, why do you think, all right, so if, for example, I were to move the card very slowly, you would notice that the penny doesn't fall. So let me go ahead and show you what that looks like if I can find my webcam. If I were to move my card very slowly, all right, you would notice that the penny actually stays on the card. Okay? So what is it about the fact that I flicked the card that made it so that I was able to move from underneath the penny? Yeah, exactly, Caden. So I had to use some amount of speed, right? So we're going to learn a little bit later that the reason the penny is stuck to the card is because of something called friction. And by using enough speed, I could actually overcome that friction in order to keep the penny from being moved by the card. Smiley faces emojis in the chat box if that makes sense. I had to move the card fast enough to overcome the penny's friction. Excellent. All right, let's go ahead and not drop my webcam this time, and let's move on here. All right, so let's talk a little bit about gravity first. So the force due to gravity is an attractive force that is found between all objects. Now, all objects, all physical substances have mass, and therefore anything with mass actually does have its own gravitational field. It is always an attractive force, so things with mass attract other objects. This actually means that you do exert a small amount of gravity on other people. And pointer, hint, this means that you are actually always attractive. So if you're ever feeling bad about yourself, remind yourself that you are always attractive because you have a gravitational force. Go ahead, give me a smiley emoji in the chat box if that makes sense. Everything with mass has a gravitational field. Now, the thing is, your gravitational field is a little bit smaller than the Earth's, so obviously people don't fall towards you very often. But on Earth, if you were to jump off, you would fall back towards the Earth. And the reason for this is because Earth is extremely massive. It is very, very large. And so this has a huge gravitational force that pulls things towards it as you try to leave the Earth. It's really difficult to get away from the Earth. You just fall straight back down. So the force due to gravity is also sometimes called weight. So we label it in two different ways. We can label it as Fg, which means force. G means gravity, force due to gravity, or sometimes it's labeled as W meaning weight. Now, forces are measured in a unit called newtons. We're going to learn more about Sir Isaac Newton tomorrow, but he was a very famous scientist, mathematician throughout history, physicist, who talked a lot about gravity. So this is measured in the units called newtons. Newtons or pounds are both examples of how you can measure weight. Again, we'll be using newtons mostly in our science class because newtons is a more universal unit, but 1 newton is the same as 2.2 pounds. So if you take a look here, the way I would draw this is I would draw an arrow downwards, labeling it as Fg, force due to gravity, pulling down on the object. And in this case, I'm just going to say this one has a weight of negative 20 newtons. Negative because force due to gravity is going down, which is the negative direction. Green checks, orange X's if that's beginning to make sense. Excellent. All right, looks like I got most of you. Let's go ahead and take a look at number 2. This is number 2. Go ahead and fill in the blank with the word attractive, only the word attractive. You have 20 seconds to raise your hands for number 2 in your notes. So let's go ahead and try this out. So what is the force due to gravity? Where is the force due to gravity occurring in this demo? Again, tell me, which way should I draw the force due to gravity? Should I draw it up, down, left, or right? Tell me in the main chat. Which way should I draw the arrow for the force due to gravity? Thank you, Joseph, Cody, Jonathan, Shayna. I see you all in the chat. Perfect. Let's get some more answers. Which way should I draw gravity? Yes, Kalina. Yes, exactly. It's going to be downward. So I'm going to go ahead and just start it at the penny. And the force due to gravity is pulling the penny downwards. Remember that we actually want to label this as F for force with a little g for gravity. So we can see the force due to gravity pulling down on our penny. Now this is not the only forces involved, so let's go ahead and learn about some other forces as well. But again, force due to gravity will be pulling the penny downwards.
The force due to gravity, right? If we think about this logically, right? If the only force acting on the penny just sitting on the cup was the force due to gravity, then the penny, as with this purple square here, it would just fall continually downwards. However, the reason why it doesn't fall is because there is an opposing force pushing up against the downward force of gravity with the same intensity. This is called the normal force. So the normal force is defined as the support force a surface exerts on an object. It is always perpendicular to that surface, meaning that, as we can see here, perpendicular meaning that it is 90 degrees to whatever surface it is on. And also some or all of normal force works against the gravity. For here, we're being asked how much normal force is needed if we have the force due to gravity being negative 20 newtons. If the weight here is negative 20 newtons, how much force in the normal force do we need up here? There we go. Thank you, Timothy. Thank you, Jonathan, for fixing your mistake. Yes, it is 20. So for number 3, it's going to be the support force, and our normal force is going to be plus 20 newtons, because if I take 20, positive 20, and add that to a negative 20, 20 minus 20 is going to be 0, and so that makes sense for an object that's just sitting there on a surface with no movement, because the net force, or the summation of all the forces, is coming up to 0. All right, so for number 3, go ahead and raise your hands when you're ready to move on for number 3. All right, so the normal force here acting on the penny is acting against the force due to gravity. If I'm going to draw the normal force acting against gravity, which way should I draw it? Should I go up or down? Tell us in the chat. Yes, it should be going up, exactly. So I'm going to draw an arrow going up just like this. Of course, if we had a magnitude for the force due to gravity, I would label my upward arrow with a magnitude also, but for now we can just label it as F sub n, just like in the previous example. All right, so now learning something called the applied force. The applied force is a push or pull on an object by a person or another object, right? So we can think of us pushing a box, or if you ever want to play billiards, right? You're hitting a billiard ball against another ball that transfers the force so you can make it into the pocket. All right, but generally we're learning about right here a rule called that when at rest on a surface, applied force will begin to move an object once it overcomes friction, right? So just like the penny experiment that we just did. All right, we'll learn more about friction in a later slide, but over here, just notice how that the applied force is bigger than the friction force, and because of that, it will begin to move. So we have normal force counteracting the force due to gravity here, but because the net force on the horizontal direction of the applied force is greater than friction, that's why the object will begin to move in the horizontal direction. All right, number 4 is going to be applied force. All right, spell applied. For number 4, please raise your hands again when you are done with that question.
All right, let's go ahead and actually begin to put this on our diagram. So taking a look here, assuming I flick the card towards the right, which way should I draw the applied force? The applied force is the force that I am applying to the card in this case, Go ahead and tell me in the chat, which way should I draw the applied force? Up, down, left, right? Tell me in the chat. Again, I flicked the card towards a certain direction. Applied force is the force that I apply to the card. Perfect. Yeah, exactly. So we actually moved the card right to the right. All right, so this would be our applied force, right? So I'm going to go ahead and mark this as my F. Sorry, let me actually just draw it out. Right, so I'm going to go ahead and mark this as my F with a little a, or we can sometimes put the word applied here. All right, so the applied force pushed the card to the right. Smiley faces emojis if that makes more sense. Smiley face emojis if that makes more sense. Go ahead and tell me in the chat box. Again, applied force is the way that I push the card. Again, we didn't push the penny, I pushed the card. Awesome. All right, let's go ahead and now take a look here. Again, so we have force due to gravity working on the penny. We have the normal force preventing the penny from falling, and the applied force being applied to the actual playing card.
Poses motion of an object, right? So mostly when we talk about friction, we're mostly going to talk about it in the horizontal plane, but there could be in some circumstances friction that is applied in the vertical direction. But in this diagram right here, we can see that there is a pushing force, or we could also call it an applied force that's pushing this block towards the right-hand side. All right, we know that it is overcoming the friction because we can tell by the diagram that it's telling us that the motion is going in that direction. But we can see that because there is some amount of friction that's opposing that force, that the actual motion of the block is not as great as the magnitude of the original pushing force. All right, so that's about how friction works. It opposes whatever force that we're pushing against something with. Why is friction helpful, right? Well, friction is basically allowing us to do whatever we're doing right now in class, right? We're sitting at our computer, we're typing on our keyboard. If we walk across the room or we turn the page of a book, everything that we have that we can like grip or slide against something with, friction helps us to not just slide all over the place, and it helps us get some grip on reality in our own world, all right? So, but yeah, the diagram down here does show how our feet work when we walk. We apply a force backwards against the ground, and the ground applies a static frictional force against us as we push our foot to walk forward. All right, that's why friction is very helpful. So for number 5, go ahead in your notes for number 5, write opposes spelled as you see there.
All right, so let's go ahead and then take a look here. So again, the card here is moving to the right. Friction is going to oppose that motion. So which way should I draw friction? Up, down, left, or right? Tell me in the chat. If it is opposing the motion, the applied force, which way should I draw the friction? Excellent. I see Cody. I see Angelina. Yeah, so since the card moves to the right, the opposite, the opposing force from friction would be to the left. Now that friction is occurring between surfaces, so it's occurring between the penny and the card. So this is going to be our force due to friction. And I'm going to draw it a lot smaller because remember, we were actually able to overcome that force due to friction. We were able to remove that card without it affecting our penny because we applied a large enough force here. Our force applied was much larger than our force due to friction. All right, so we can see this kind of overall diagram here. Again, force due to gravity pulling down on the penny, normal force preventing it from falling. We apply a force on the card to the right, and friction tries to prevent that card from moving. Friction force, though, is too small, and so we were able to overcome friction.
Our first type is known as static friction. So static friction is the resistance force between two non-moving objects. So in just terms of language with the definition, static just means that you're not moving, right? There's static motion and then there's like moving motion. So static friction is just the resistance when something is not moving. It prevents an object at rest from moving across a surface. Otherwise, you can think of it kind of like a piece of melting ice on a smooth surface. You can think of something like that as it slides around, or maybe like an air hockey table, something like that has that type of behavior is something that has no friction. All right, so it's important that we do have this static friction, or else we would just be sliding everywhere.
Okay, so static friction occurs between objects that are not yet moving. All right, kinetic friction, though, happens once things do start to move. So again, the force is going to resist whichever way the object wants to move. So even when something is static, like for example, when you're trying to push a refrigerator and the refrigerator does not want to move, if you're trying to push the refrigerator forwards, the refrigerator, even though it's not yet moving, static friction will still try to push backwards on it. Smileys, emojis in the chat box if that makes sense. So whether it's static or kinetic friction, it's always going to work against the way that the object wants to move, whether or not it's yet moving yet. Awesome. I see smileys. Tati, Jayland, Angelina. Great. So kinetic friction, though, is once it's actually moving. So for example, once that fridge does begin to slide across the ground, now we have that static friction turning into kinetic friction, and kinetic friction will resist that motion. Now, the interesting thing about kinetic friction is actually smaller than the maximum amount of static friction. This should make sense, though, because once you start moving a refrigerator, does it get easier or harder than as you were just trying to start it pushing? Once it actually starts moving, does pushing it get easier or harder? Tell me in the chat box. Excellent. I see an answer from Caden. Still waiting on more participation in the chat. Once the refrigerator starts to move, does it get easier or harder to push? Yeah, it actually gets easier to push, all right? So once things start moving, that kinetic friction is actually a little bit smaller than the static friction, and that is why things feel easier once they actually start moving. So again, static, you should think it stays in place, right? It has those same 5 letters right there. So static, you should think it's when the object stays in place. Whereas kinetic, we know the word kinetic means motion, so you should think of that as when the object is actually in motion.
At rest from starting to move, while blank friction resists the motion of an object that is already moving. So we have a multiple choice of 4 answers. All right. The first answer before the comma is going to be that first blank, and the second answer in each choice is going to be after the comma is going to be for the second blank. So we have a choice between static, static, kinetic, kinetic, static, kinetic, or kinetic then static. So take your time and put a box, I'm sorry, let me turn your whiteboard tools. There we go. All right, put a box around the answer that you find most suitable using your whiteboard tools. All right, the first type of friction that it's mentioning prevents an object at rest from starting to move, while the second one is in motion. So those are the keywords, rest and motion. So for this one, the answers are going to be static and kinetic in that order for number 6.
This last question, now we just need to go ahead and take a look at what we've been practicing throughout the entire lesson and just go ahead and apply it. All right, so you need to go ahead and match each force to its correct label on the diagram, right? Applied force, remember that was our push or pull. The force due to gravity, remember that's an attractive force that pulls things towards Earth, right? Sorry, let me annotate this up here if my tools will work. Right, no? All right, towards Earth. The friction force is going to oppose motion. So think about which way the card was trying to move, right? So this opposes motion. And then don't forget that the normal force is going to oppose gravity and prevent things from falling. So normal force opposes gravity to prevent things from falling. All right, this is going to be helpful for number 7. Go ahead and raise your hands when you have number 7 complete. You have 45 seconds to work on that. Raise your hands, raise your hands. Here, so we talked about force due to gravity, normal force, applied force, and the 2 types of friction force, and we learned how to put those on the diagram. Go ahead and let us know in the chat if you got A's or B's. We want to shout you out. And then don't forget that you need to make sure you're getting your projects done. Those have been zeroed out for people who have not yet turned it in. So please make sure you are getting your projects done. Thank you so much, everyone.